Question 1. Use the intermediate value theorem to determine whether or not there's a solution to the function f of x equals 4x cubed minus 2x squared minus 6, or minus x minus 6, between x equals negative 5 and x equals 6. Okay, so the intermediate value theorem says that basically if we have a sign change between two values, which we're going to check x equals negative 5 and x equals 6 here. So if we have a sign change between these two values, then there must be a solution to this function. So what we're going to do is we are going to check x equals negative 5. And, we actually don't even need to fully solve or fully find these values. We just need to see whether they're negative or positive. So for this, we know that 4 times negative 5 cubed is negative 500. You can check this if you want. Minus, let's see, this is negative 5 squared is 25, so this is minus 50. And this is plus 5 minus 6. Okay, so this is obviously very negative. So this is a negative value. Now we'll check f of 6. So 4 times 6 cubed minus 2 times 6 minus 6 minus 6. So we don't even need to solve this because we know that 6 cubed is going to be very, very positive times 4. So this is going to be a very, very positive value. You can check this if you want, of course, but since we have a sign change between these two values, we know that at some point in the interval there has to be a solution. Question 2. Find the local maximum minimums of the function f of x equals 5x cubed minus 2x minus 7 using derivatives. So in order to find the local maximum, we need to take the first derivative of the function. So the first derivative of this function would just be, we just use the power rule, so 3 times 5 is 15, x squared minus this, the derivative of negative 2x is just 2, or negative 2, so we get that. Now we just need to find the value of x when this function is equal to 0. Sorry about that, let me try and rewrite that. So we'll add 2 to both sides. We get 15x squared equals 2. Divide both sides by 15. And we get x squared equals 2/15. And now when we take the square root of both sides, these will cancel and we'll get x is equal to plus or minus the square root of 2/15. So these are the maximum and minimums, the critical points. Question 3. Determine the inflection points of the function f of x equals 3x to the fourth minus 2x cubed plus 8x squared minus 7. So I'll tell you right away, this is kind of a trick question, but we'll go through it anyway to show you how you would figure something like this out. So the inflection points are the second derivative of the function. So let's take the first derivative. We'll just use the power rule in all of these terms. So we get 12x cubed minus 6x squared plus 16x. Now the second derivative, setting this equal to 0 would find the maximum and minimums. Setting the second derivative equal to 0 and solving for x would find us the inflection points. So this is 36x squared minus 12x plus 16. Now in order to solve for x here, we're going to use the quadratic formula, which states that the solutions to a function are negative b plus or minus the square root of b squared minus 4ac all over 2a. So these values all here, they refer to the coefficients on each term. This would be a, this is b, and this is c. So we're going to enter these in. We'll say x equals, what's negative b? That's 12, plus or minus the square root of 12 squared, which is 144, minus 4 times 36 times 16, all over 2 times 36. Now something weird happens here. because if we simplify what's in the radical, we get negative 2,160. The negative value here means that there's no real solutions to this function, basically. There are imaginary solutions, but no real solutions. So in effect, what this means is that there's no inflection points to the function, right? And this actually makes sense because we have a fourth term in the front here, and so it's going to look something like parabola, right? It's going to look something like this. So there are no inflection points. There's never a point at which the function begins to change curve, right? It never goes like this or whatnot. That's all I have for today. Thanks for watching.